Okay, so in this video we're going to look at solving linear recurrence relations. So remember that a recurrence relation is just a recursively defined sequence. And so just to get a couple of terms out of the way, I've quickly listed 4 recurrence relations. And if we focus in on these first two, this first example is an example of a linear recurrence relation. The second example is not linear. So what it means to be linear, it's kind of like if you think back to when you talked about linear functions. What made the function linear was that its exponent was, the variable had exponent 1. Same thing with a linear recurrence relation. So we're going to look at all of the a subscript I terms. I just say that to refer in general to a subscript n minus 1, a subscript n minus 2. I'm just calling each of those a. It's the a sub ith term. And each of those has exponent 1. And so that is an example of a linear recurrence relation. This second one is not linear because if I look at the a subscript n minus 1, its exponent is not 1. Right? This term has exponent 1, this term has exponent 1, but not this one, exponent 2. Right, so that one is not linear. And then, so 3 and 4, both linear, right, both linear. However, there is an other term I want to mention real quick, homogeneous, or homogeneous, however you want to say that. What it means for a recurrence relation to be homogeneous is that a recurrence relation is homogeneous if it consists only of a subscript I terms. So this third one is not homogeneous because we've got a subscript n minus 1, but then there's this term that doesn't have any a subscripts, right? It's kind of the odd term out, right? Whereas if I look at this fourth example, this one is homogeneous because I've just got 2 terms and both of them contain a with a subscript, right? So that one is homogeneous. One thing I've seen people do is if you get all of the a subscript terms over to the left side, then on your right side, if you have 0, that would identify a homogeneous recurrence relation. On this one, if we get all the other terms to one side, we'd still have the 3n left on the right side. So we're going to focus in on linear, homogeneous recurrence relations, and the technique for solving those is a lot less complex than if the recurrence relation is nonlinear and or if it is not homogeneous. Right, so let's take a look at this example as to how we would solve this recurrence relation. There is a nice technique, and so maybe you've done some reading on this topic, and in your book or whatever material you were reading, you probably came across some fairly complicated theorem or property that explained how to solve this, but it's really pretty simple. We're going to take advantage of the fact that this is homogeneous. We're going to get all the terms over to the left side, and so subtract 5 a sub minus 1, a sub n minus 1, and add 6a sub n minus 2. So I can clearly see that that's homogeneous and linear. And what this really boils down to is identifying what's called the characteristic. Let's see if I can spell this right. Characteristic equation. So the characteristic equation is just going to be a nice quadratic equation that corresponds to the 3 terms in our recurrence relation. So this is going to correspond to the squared term. And I have coefficient 1 here, coefficient 1 here. This is going to correspond to the degree 1 term. And this is going to correspond to the constant term equal to 0. So the terms in the recurrence relation correspond to terms in what's called the characteristic. Right? And we transform into the characteristic because the characteristic is just a quadratic. You can use whatever letter you want. I chose I chose to use T. You probably wouldn't want to use A because that's what's in your recurrence relation, but whatever letter you like. C, sometimes C is used for characteristic, I guess. But it doesn't matter. What matters is that now this is a nice factorable quadratic, and we get two solutions to the characteristic. And anytime we get two different solutions, two distinct solutions to the characteristic, that tells us that the general form of the solution to the recurrence relation is some constant times this first value to the n plus some other constant times this value to the n. Right, so I could write that in any order. I could have said that the solution was going to be b times 3 to the n plus d times 2 to the n. Right, I could have gotten the 2 and the 3 in any order, and I'd still be okay. Right, so this is called the general solution. These guys, b and d, are constants that we're going to go figure out. Right, we're going to go figure those out. And let's see if I can fit this in on this page. I'm going to apply these initial conditions to try to figure out those constants b and d. So if I apply this first condition, that says put 0 in for n. So I'm going to put 0 in for n here, in here, in here. Oops. Sorry, that should be b times 2 to the 0. And I get to set that equal to 7. So really what I'm going to focus in on is this part of that equation. Since 2 to the 0 is 1 and 3 to the 0 is 1, that's really that b plus d equals 7. Right, so there's one equation with the letters b and d. Now I'm going to apply this second condition, which will give me a second equation with the same two letters. I'm going to plug 1 in for n. And again, focusing in on this piece of the equation, that gives me that 2b plus 3d equals 16. And now I've got a system of two equations and two variables, and I'm going to solve that by elimination. I'm going to multiply this first equation by -2. Right, so I just multiplied this entire equation by -2. I'm going to keep this second equation the same. And then if I add those two equations, that eliminates b. And adding these two, I get that d is equal to 2. right? And then I can take d equals 2, plug back into either of my original two equations, so probably easiest to plug in right here. If I plug in, I'm going to squeeze this in at the bottom, plug in that plug in that d is 2, and that means that b must be 5. Right, so now I know that this is my solution, except I've found the values of b and d. So the final solution is 5 times 2 to the n plus d, which is 2 times 3 to the n. And that's the specific solution to this recurrence relation with these two initial conditions. And so I squeezed that all in on one page because I had a second example written on the second page, but I think I'll start a new video to do this second example.